Okay. Before we get started in the new material, and yeah, this is still, I like it loud, but it's 9:30 and it's Monday morning, so I don't need to do that to everybody. Why don't we take a couple minutes just to review what we've done so far, because you're all sitting there thinking, I know we had this class last week, I just know it, but I don't know what we did. So let's try to remember. Bless you. 3 components of a distribution that are important to know. What are they? Yeah. No, but thank you for answering that. Her gut reaction was mean, median, and mode. What are those, by the way? Those 3 are what? Measures of central tendency, right? Yeah, all the way in the back. The what? Yeah, center, shape, and spread, right? Those are the 3 components of a distribution that I want to know in order to know everything about the distribution. Of center, let's not stand there, shall we? Of center, we know it's the mode, the median, and the mean. And do we want to turn it down a little? Is that what we're thinking? Okay. I like not having to strain. Is that better? I did lower it. Okay. So those are the measures of the center. Okay. What's another term for the measures of spread? Variability. Dispersion, right? Measures of dispersion. Okay. What's a measure of dispersion that's not prone to being influenced by outliers? A measure of dispersion that's not jerked around by extreme scores. Yeah. Yeah. Yeah, the SIQR, the semi-interquartile range. Okay. Here's a question. What is a standard deviation? We're going to be doing this all semester. And everybody, the truth is, in these classes, everybody can do the computations. You know, pretty much everybody can plug in the numbers. But then I ask people, well, what is a standard deviation? And they're like, I have no idea. What is a standard deviation? What's a standard deviation? Yeah.
Isn't that like the amount, like the range that's, if you have whatever the mean is and you're allowed a certain amount of points?
You're getting there. You're mentioning a couple words that work, but let's get a more, yeah. Yeah, right? How far on average scores are spread out from the mean? It's good to remember that. It's good to keep that in your brains, that that's what it is. Because like I said, we're going to be referring to it a lot. So you don't want to have to keep thinking, yeah, what is it again? It's an approximate amount of how far scores are spread out from the mean. Okay, how does a standard deviation calculated from a population differ from that calculated from a sample? What's the only difference? I mean, yeah, one is in Greek letters, one is not. Yeah. It's unbiased, meaning what? Yeah, it's divided by, she said n-1, which is true for this one group. But what's the more generic term we use? Yeah. Degrees of freedom. Degrees of freedom. Because that's going to change. For one sample, it's definitely n-1. But it's going to change when we have more than one group or depending on various situations. Okay, yeah. Well, if you look at the formulas, will have it, but it's S. It is S. It's the sample standard deviation. Because try to remember it this way. We're using degrees of freedom because we're estimating, we're using our sample to estimate what's going on in the population. That's why we have to make the adjustment. Because if you have your population, you can just calculate the numbers. It's not a problem. But if you're trying to use a sample to estimate what's going on in the population, because you don't know what's going on in the population, then you have to make that adjustment. Okay, questions? Questions on any of that? Is that bothering anybody? Stuff should be reasonably straightforward. All right, and then the last concept we talked about was the shape of a distribution, right? The shape of a distribution. And we talked about positive and negative skew, right? Let's say I give an exam, and unfortunately, it's very, very, very difficult. All right? If it's going to be skewed, which direction do we think it's going to be skewed in? Yeah, it's likely to be a positively skewed distribution. Why? Yeah. Okay. Okay. Why will the scores pile up at the bottom? Like, why won't it just be kind of normally distributed at the bottom? Why will they like jam up against the bottom there? Yeah. Yeah.
The score can't go below 0.
Yeah.
So it's not like really.
Yeah, blessedly, your exam scores can't go below 0, right? So they can pile up on the bottom because they can't go lower than that. That's a floor effect, right? A floor effect versus a ceiling effect. Okay, now I believe we had left off. Had we done this already? I couldn't remember if we did that or not. No, right? Okay, let's take a look at this little cute little picture for a moment. Imagine I own a company. And these are the salaries of everybody in the company. You can guess which is mine. Okay? I can dream, all right? I can dream. So first of all, bless you, what kind of distribution is that? Is it a normal distribution? Yeah. It's positively skewed. It's positively skewed. Why? Why is it positively skewed? Yeah. Yeah, but why is it skewed, I guess, is really the question. No, let me see how to ask this. Why is it positively skewed versus negatively skewed? Maybe that's the way to ask it. Think what the values are. It's income, right? Someone want to help her out? Yeah, it's part of it has to do with the way I ask questions. Yeah. Well, that's how we know that there's skew there. But what's causing it? Yeah. Yeah, you can't make less than $0. Right? There's a floor effect there. There's a floor effect there. Now, if I wanted to find the measure of the center of this distribution, we have 3 options here. Which is the right one? Which is the right? Oh, see, now you're starting to get smart. You're being a little cautious when I ask you questions, right? Yeah. She says the mode. Anyone have issues with that? Anyone want to make a suggestion? Yeah. He suggests the median. Anybody want to offer the mean? No, everyone's like, no, I don't think so. Okay, well, first of all, are all of these 3, are they all accurate? They're all accurate. They're all technically accurate. Each of those numbers is calculated correctly. But are some of them more representative than the others? Well, yeah. Well, you know, imagine I'm getting interviewed by a magazine because somebody thinks I'm a really great employer. Right? And they say, well, what's the average salary of your employees? What might I say? Well, I might say the mean. But that would be misleading, wouldn't it? Because no one actually makes that value or anywhere close to it. Now, what if you're one of the people making $14,000, okay? And a friend of yours wants to get a job at my company. What might you report? Well, you might report the mode, because that's the most commonly occurring value. But you also might report the median, okay? Because, again, the median is not jerked around by outliers. So that is the most common measure for income, is the median. So if somebody's trying to talk to you about income statistics and they're calculating a mean, if they're giving you a mean, don't buy it. Don't buy it. Try to investigate further. Yeah?
We only refer to the mean as the average, or we can refer to all 3 as an average.
So he said, right, the term average, if you say average, people tend to think what you're talking about is the mean, okay? It's kind of an amorphous term. It's kind of an amorphous term. People might use it for the median. I think they rarely use it for the mode, but they might use it for the median. So you might want to push, you know, when they say average, what exactly do they mean? Okay? So yeah, and what's the measure of central tendency I would use for these statistics? The measure of dispersion I would use for these statistics, if I'm using the median as the center. What's the measure of dispersion that I'd be inclined to use with it? Remember, they go together. Yeah. Yeah, actually, technically, the SIQR, the semi-interquartile range. Even though the interquartile range is there, the semi-interquartile is the one that's used. Okay? So that is all we need to say about those measures. Now let's talk about, for a couple minutes, properties of the mean and the standard deviation. The properties. As I mentioned to you before, right, a mean works like the fulcrum of a seesaw, with the distances of the scores above and below the mean balanced out, right, by the fulcrum of the seesaw, which is the mean. So let's talk about what happens. First of all, what happens if you add or subtract a constant to every score in the distribution? What happens to the mean? Yeah, right? You add or subtract the same amount to the constant. It's the same thing. Imagine I give you guys an exam, and then I come in and say, okay, question 13 was no good. I'm adding 2 points to everybody's score. What happens to the mean? It's also raised by 2 points. Okay? What about if I multiply or divide by a constant? Again, every score in the distribution. What happens to the mean? Yeah, the same thing. It's also multiplied or divided. Again, imagine I give you an exam and it's out of 50 points. But you want to know what your score is out of 100. So you multiply by 2. Well, that multiplies the mean by 2 as well. Okay? This third thing, we've talked about the sum of the deviations from the mean will always equal 0. That's called, anybody remember? The fact that all the deviation scores will add up to 0. Yeah. Yeah, the zero-sum principle. The zero-sum principle. And then the last thing here, the sum of the square deviations from the mean will be less than the sum of square deviations around any other point in the distribution. Okay, let's put that in English. When I found the mean, I said I could find deviation scores from the mean, right? How far each score is away from the mean. I didn't have to use the mean. I used the mean, right, to find the standard deviation. But I could have used the median. I could have used the mode. I could have used the highest score, the lowest score, right? I could have used any single point in the distribution, yeah? But I didn't. I used the mean. Why? Because if I find the deviation scores, right, and I square them and add them up, it'll be smaller, which, by the way, take deviation scores, square them, and add them up. What's that called? Sum of squares. Sum of squares. It'll be smaller if I take those deviation scores from the mean than if I tried to do it from any other point in the distribution. Okay? Which is one of the reasons why we do it. You wind up with less variability. Less variability. Meaning, by the way, sorry, just a second, that the mean will be more representative than it would be from other scores. Yeah?
Can you say the statement of why again? Because I didn't quite hear it.
Of why?
Why you use
Oh, no, just that I'm not sure I'm going to get this quite right, but stop me when I keep talking. That you get smaller a sum of squares from the mean than you would from any other point in that distribution. You get less variability, essentially less variability. Okay? What about the standard deviation? I add or subtract a constant to every score in the distribution. What happens to my standard deviation? You can read it. Yeah. They don't change. The standard deviation doesn't change, right? Because what you're doing is, if you add, again, go back to my example. I add 2 points to everybody's score in the distribution, everybody's score in the class. What happens is you move the distribution this way or this way. But you're moving the entire distribution. You're not making it narrower or wider when you add or subtract a constant. Okay? So the standard deviation will stay the same if you're adding or subtracting a constant. What about if you're multiplying or dividing? That will change it. If you multiply or divide by a constant, bless you, that will change the standard deviation by the same constant. So for example, again, right, let's say I have 2 scores. I have an 8 and a 10. What's the difference between those 2 scores? 2 points, right? If I multiply both of them by 2, now what do I have? 16 and 20. Now the difference between them is 4 points, so I'm spreading it out. Okay? So that's multiplying and dividing. And then lastly, the standard deviation from the mean will be smaller than the standard deviation from any other point in the distribution. That's what I've just said. That's what I was talking about, the mean. Right? Now, that characteristic of the mean, that the sum of squares is smaller from the mean than it would be from any other point in the distribution, makes what we call the mean a least squares estimate. You got that term? A least squares estimate. It's just a technical way of saying that the sum of squares from the mean are smaller than any other point in the distribution. It's a least squares estimate. Okay. All right. So those are the basic characteristics and things we want to talk about. Now we're going to go back to one more graph, which actually is here because it uses the median. And it's an interesting little way of illustrating your data. They're called box plots or box and whisker plots. And it uses the median and the IQR to indicate the center and spread and shape of a distribution. So you get all 3 components in this very, very brief little picture. Okay? This is part of, again, what we talked about as exploratory data analysis. You know, when you collect data, you get all these numbers. And everybody thinks, we're under this impression that we get this beautiful, pristine data set where everybody's answered, and everybody's answered to the best of their ability, and, you know, and that it's really nice and pretty and clean, right? We'll talk about data as being dirty or clean or noisy, right? Like I used to work with babies. You know, we would find babies in vision, and so we might time where the babies are looking. So babies are very interesting when you deal with them. Babies will look at something, they might look at something else, they'll look, then they'll look here, then they'll look here, then they'll look at their toes, then they'll scream. Okay? That winds up in data that we call noisy, meaning there's a lot of variability. There's a lot of variability in it. So one of the things that we do is we look at our data before we try to crunch numbers with it to see, do I have outliers? If I have outliers, what does that do to? You can get outliers for a range of different problems, from typos, right? You're typing in numbers and you do that incorrectly, to equipment problems. One of the things we did with babies was look at eye tracking. And this was a long time ago, so the eye tracking equipment wasn't the same caliber we have now. And we could go through entire sessions and then find out that the machine wasn't working properly, which was not fun, I have to tell you. Okay? So that could be equipment issues could give you outliers. Sometimes people don't follow instructions. So I would beg all of you, follow directions, folks, right? So sometimes people don't follow instructions and you get outliers and you get all these weird scores. So you want to check this stuff and deal with it before you try to play with the numbers. Okay? So one way to do that, one part of exploratory data analysis is you can do these box and whisker plots or box plot. So let's go through all these terms so we know what's going on here. So what I've graphed here are the bloomers and the others. Now one of the nice things about a box plot is I can put different distributions on the same graph. That's really nice. All right, let's take a look. Let's look at the bloomers first of all. Okay? You see the box? The line in the middle is the median. The line in the middle of that box is the median. If it doesn't fall in the middle of the box, that means that your distribution is asymmetric. It's asymmetric. All right? Now, let's talk about the top of the box and the bottom of the box. Those are called the hinges. The top of the box and the bottom of the box. Those are the hinges. Loosely, It's the 75th and 25th percentiles, or the first and third quartiles. And I say loosely because you might find slight variations depending on the book you read, depending on the computer program. But for our intents and purposes, 25th and 75th percentiles is just fine. Okay? So up here would be the 75th percentile. Down there would be the 25th percentile. Let's find it for this example. Let me put those numbers in for you. Okay? So for the bloomers, this upper hinge is 22, and the bottom hinge is 6. Whereas for the others, the top is 13.5, and the bottom is 0.5. Okay? The distance between those two hinges, the length of the box, that's called the H-spread. That's called the H-spread. And guess what it is? Can anybody see what the H-spread is, by the way? Not the number, but what it is. Almost, the IQR. It's the IQR, right? The SIQR divides it in half. It's the IQR. So the H-spread and the IQR are essentially the same. Okay, let me give you that number. So the H-spread for the bloomers, what's the H-spread for the bloomers? The H-spread for the bloomers. You guys can do this math. I know you can. Yeah. And for the others? Yeah. Okay? That's the H-spread, and we're going to use that for a minute, in a minute. Okay? It's essentially the IQR, but it's the H-spread in this context. If you're talking about what the box plot looks like, it's the H-spread. That's what the IQR is. Yeah. No, it's okay. This is, good enough. Okay? All right. So now let's talk about what the inner fences are. Because what I want to do is I need to set up ways to understand what are outliers and what are just large scores or extreme scores, but what are outliers. So we do that by setting up these inner fences. Okay? The inner fences give us this range. So what's an inner fence? An inner fence is going to be 1.5 times the IQR added and subtracted from the hinges. So let's go through that. Okay. Let's do the bloomers. Let's see. Okay. So 1.5 times their H-spread. Their H-spread was 16 equals 24. Okay? Let's just find the numbers and we'll go back and make sure we understand what this is. Right? So for the lower fence equals 6 because that's its lower hinge, right? 6 minus 24. And then the upper fence equals, what was the upper hinge? 22. So those are the inner fences for the bloomers. Now what are those inner fences? Those are essentially the guidelines for what constitute an outlier. So if you get a score that falls outside of those fences, either larger than the topmost or smaller than the bottommost, that's an outlier. It's not on your graph. It's not on the graph. If you were actually going to create the graph from scratch, you might put them in, but it's not on that picture. They don't generally put them in SPSS. What are there, though? The whiskers. Let's take a look back at this for a second. Okay, we have our boxes. Look at those, the lines, those vertical lines, those are called the whiskers. That's why it's a box and whiskers plot. The end points of those whiskers are called adjacent values. Those are the adjacent values. the farthest most points of those whiskers. So how do you get those whiskers? They're the most extreme scores in the distribution that are not outside the fences. Would you like me to repeat that? They're the most extreme scores in the distribution that are not outside the fences. Right? Because what that shows you is, what those whiskers show you is the minimum score and the maximum score. And then if you'll notice, like there's a score here, that value. It's not 12, by the way. It's probably its case number. But that score out there, that's an outlier because it falls outside. It's not the, right? You would think, oh, maybe that should be the tip of the whisker. But it's not because it falls outside the fences. Right? If we put in our numbers for our fences, what were they? 18 and 46? That's a minus 18. Nobody caught me on that. Right? This is minus 18. Right? So let's say it's about down here. And 46 was about there. Okay? Those are our fences. So this person up there, they fell outside the fences. So they're an outlier. Okay? Questions? Clarification? Yeah? Oh, it's interesting. I don't know. There's probably a real history to it. But in some respects, my guess is that it's arbitrary. That somebody had to come up with some kind of objective value for what's going to constitute an outlier. So often it's like 1.5 times the H spread is just kind of typical. Okay. What else? Anything else that's clear? Yeah? Okay. You guys are fast. Okay, good. So this is basically your box plot. So you can see what your outliers are. You can see whether you have a symmetrical distribution or not. You can see where your median is and your first and third quartiles. You have essentially your center, your shape, and your spread, and you have them next to each other. So it's a real fast way of seeing what's going on. Okay? All right. I think we're done with that. Yeah, go ahead.
What was that, the middle line?
The middle line in the box? That's the median.
Okay.
And if it's not in the center, then that means your distribution is asymmetric. Okay, so if you find out you have outliers, what can you do with them? Yeah? The definition for inner fences is essentially 1.5 times the H spread added to and subtracted from your upper and lower fences. Your upper and lower hinges, sorry. Your upper and lower hinges. Okay? Good. All right? Okay, so you get these outliers, and then the question is, oh yeah, still? The IQR. The IQR. Yeah. Yeah. Okay. All right. So you got these outliers, and the question is, how do you deal with them? There are times that you're stuck with outliers, right? You might have an extreme score, but there's no justification for getting rid of that number. That happens. That happens all the time. You know, like I said, working with babies and things like that, you get some really far-off numbers, but you have no reason to say, okay, let's delete this. Sometimes you do. Sometimes it's obvious. You know, somebody fell asleep during an experiment. You can, you know, not use their data, unless there's lots of people, in which case you might want to rethink your experiment. But in general, you know, you have to have really good justification. So if you feel justified in omitting outliers, what are some of the techniques that you can use? Well, one of them here, trimming. Trimming. And trimming is exactly the way it sounds. You take a little off the top and a little off the bottom. You decide on a percentage of extreme scores that you're going to omit from the top and the bottom. And you do that simultaneously. And you can't say, I guess I'll take 3% off the top and 1% off the bottom. It's going to be the same amount. Okay? That's called trimming. And if you calculate a mean afterwards, right, you trim your scores and then you calculate the mean, that's called a trimmed mean, a trimmed mean. And it is robust, or one could say resistant, right? Not influenced by outliers. Windsorizing is another technique of dealing with outliers in which you don't delete the uppermost scores and the lowermost scores. What you do is you decide on a percentage, and then you replace the numbers. You replace them with the most extreme score that you're not changing. You replace them. So for example, if I've decided that anything over 10 is going to be an extreme score, right, as an outlier, and I'm going to windsorize, what I do is replace all the scores above 10 with the number 10. And of course, you do that separately for the top and the bottom of the distribution. That way you don't lose the numbers, but you don't have these outlier numbers either. Yeah? Yeah, let's say you have a distribution of scores, and you've decided that any number over 10 is going to be an extreme score. And you have a 13 and a 15, somebody got a 17, all right? So what you do is instead of deleting those scores, which would be trimming it, you would take those 3 scores and replace them with 10 because you've decided that 10 is your upper limit. Is that better? Yeah? Okay. Yeah?
Do you have to replace the same amount of scores on the top and the bottom?
Not necessarily. Not necessarily. It's kind of, you know, some of this really depends on what measuring instrument you used. You know, that's really an issue. Okay. All right. So that's windsorizing. Using a trimmed mean may affect advanced statistics. Again, once you're not including everything, then you're not including everything. So it may be a problem. So you should just keep that in mind. Another way of dealing with outliers, data transformation. When you're transforming data, or even if you're dealing with outliers, what you're trying to do is 2 things. Deal with outliers that could be there for no good reason, and also trying to make the distribution more symmetric. Those are your goals. Those are your goals. So there are different types of data transformation that you can use to achieve those goals. Some of them are more understandable than others. All right? A square root transformation, you take the square root of every number. That tends to minimize the impact of extreme high scores. A log transformation or a reciprocal transformation. All right? Those are 3 different types of transformations. We're not going to learn them. You're not going to use them. But you should know that they're there. And you should know that if you're doing research and you have these outliers you don't know what to do with, or you have an asymmetric distribution, you might want to think about a data transformation. And it'll depend on the discipline and the measuring instrument that you're using as to which transformation you use. Okay? Now, you can't do a transformation if you look at your mean afterwards and say, I don't like that. I really wanted my mean to be higher. You can't do stuff like that. It's only to re-express it as a more symmetrical distribution. Right? So those are the basics on data transformation that I want you to understand. It's a whole other field in and of itself. Okay, and I believe that's it for chapter 3. Anybody have questions on that? I think we're good on it. All right, so breathe, stretch, sneeze yet again. Yeah. 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 Yeah.
If it's not influenced, if it is influenced by what you trim, then why is it robust?
No, it's robust. She's asking about the trimmed mean. It's robust, meaning that it's not affected by outliers, essentially because there are no outliers there to affect it. Right? Your mean has changed to a trimmed mean. And by the way, folks, whenever you're reporting this information, like if you're writing up a paper or something, you have to report that you did these things. Just as a little side note, you have to tell them, yeah, I threw out half of my data set. You got to do stuff like that. Okay? All right. Okay, now we are moving on to chapter 4. Now let's say it's midterms time. And I'm sorry, I know you're not there yet, so I hate to scare you so early on. All right? And you call your folks, and your mother says, okay, well, how'd you do in physics? And you say, well, I got a 60 in physics. And she starts throwing a fit, right? But before she gets too into the fit, you say, no, don't worry. The mean in the class was 50. Actually, I did quite well. And she's like, really? And you're like, yeah, really, because it was above the mean. I did fine. Okay? And she says, well, how'd you do in history? And you say, well, I got an 82. And she says, oh, very good, an 82. What you don't tell her is that the mean in the class is an 85. Okay? What have I just done there? What have I just done? I've just talked about my score with respect to its location in the distribution. Because that's what I really want to know, and that's what you always want to know. Anytime you get a score, your first question to me is always, well, what was the mean of the distribution? Right? Because you want to know where your score is with respect to the mean and to everybody else. Yeah? So what we're going to be talking about is measures of location, how you find location of scores in distributions. Now, let's talk about IQ for a minute, because IQ is an example that comes up a lot because the numbers are easy to work with. The mean of IQ is 100 with a standard deviation of 15 points. Sometimes people will report it as 16, I think, depending on the test that's being used. But generally, it's 15. We will use 15 because it's a nice number. All right? So if I said that somebody has an IQ of 115, what do I know about this person? Well, first of all, I know it's above the mean, right? I know that it's 15 points above the mean. But now I know another way of expressing it, okay, with respect to the standard deviation. I know that a score of 115, an IQ of 115, is one standard deviation above the mean. That is called a Z-score. A Z-score. Another name for a Z-score is a standard score. A standard score. Because what you're doing is you're taking any score you can think of, height, weight, reaction time, statistics, exam scores, anything, and you're putting it in a kind of standard format. That is, how many standard deviations above or below the mean is my score? If it's positive, I know it's above the mean. If it's negative, I know it's below the mean. So this is really useful because I can compare any distribution by changing the numbers into Z-scores. And there's going to be another use for it even further on. Not too far on, but. So let's take a look. Let's take a look at this example first. Okay? And this is John. John has 3 midterm grades. And what you need to know when you look at these grades is you need to know the mean of the exam he's talking about, and you need to know the standard deviation. So the formula for a Z-score is very simple. It's how far, because this is what we just talked about. It's how far is my score from the mean divided by the standard deviation. How far is my score from the mean in standard deviation units? That's it. So for example, John's score in psychology, he got a 68. I know it's going to be a positive Z-score because the mean is lower than that. And I find it, and it's 0.5. So I know that John scored half a standard deviation above the mean. Okay? Like I said, so that's useful at the moment, but it's going to be even more useful later on. All right, let's find out what about math? You can do it without even calculating it. 0, right? Because he scored at the mean. He scored at the mean. By the way, the mean of a z-score distribution is 0. The mean of a z-score distribution is always 0. The standard deviation of a z-score distribution is 1. So the mean is 0. The standard deviation is 1. Always. Always. Okay? Or a standard distribution. Z-score distribution or a standard distribution. All right, let's do the history one. So I know that even though John got the highest absolute score in history, really he did the worst in that. Okay? Now, here's a little interesting anecdote. You know, z-scores in and of themselves have some value, but they're going to become more valuable in a minute. But I was on the phone with a doctor because I needed to get some test results. And she was a little hesitant with me. She said, well, do you know anything about statistics? I said, a little. And she said, and she proceeded to give me my test results in z-scores. Who'd have thought, right? But because I had some idea of what a z-score distribution is, I had some understanding of where I fell, right? Where the location of my score was in that distribution. So that was useful. It was like one of those bizarre moments where you think, oh, this has some real world value. You know? Okay. Now, actually, I want to go back to that in a minute. I want to finish this because I started talking about it. The mean of a complete set of z-scores is 0. The standard deviation is 1. This one I want to talk to because while we're here and I'm talking about the location of the score in a distribution. If you change all of your scores, right, all of your raw scores into z-scores, you do not change the shape of your distribution. This is kind of an important little concept. It sounds like real obvious, but it's an important concept. If you change all of your scores into a z-score distribution, you do not change its shape. You don't change the location of any of the scores. They stay in the same place relative to each other. Often people will do research and they won't get a normal distribution and they'll say, well, can I change my scores into z-scores? Will that fix it? No, it doesn't fix it. And this goes, yeah? Okay, well, first of all, why would we change the raw scores into z-scores? The simple reason right now is so that I can compare different distributions. Right? Like John had different distributions for his midterms. But I can put them all in the same metric. Here's another example. If you take a child, you know, when they're little, you take them to be weighed and, you know, see how tall they are measured. Right? And very often, the doctor will give you results in percentiles, but essentially what you want to know is you're comparing locations because they could give it to you in z-scores just as easily. Well, this child scores 1 standard deviation above the mean in height, but 2 standard deviations above the mean in weight. So what does that mean? Okay. Now, here's the little teaser. What's going to make it more obvious as to why we transform things into z-scores is that once we transform things into z-scores, we can find out the probability of the results, the likelihood. That's where it's really going to be useful. How likely is my result? Right now, I can just compare these distributions. But in a little bit, we'll be able to say, oh, an IQ of 115. That's a z-score of 1. How likely is that? That's going to be really useful. Okay? So just to get back to the point about changing the shape of the distribution, all right? Here's a little kind of generic rule. A linear transformation of your data, a linear transformation, does not change the shape of your data. Linear. A linear transformation is a transformation where you're adding, subtracting, multiplying, dividing by a constant. Adding, subtracting, multiplying, dividing by a constant. That's a linear transformation. Right? A nonlinear transformation might be something using exponents or square roots. And that does change the shape. Those are those transformations that we talked about before. But nonlinear doesn't change the shape. So when I look at my z-scores, all I'm doing is seeing how far is my score from the mean. That's a subtraction, bless you, and dividing by a constant. So that is a linear transformation. So I just wanted you to get that generic rule in there. Okay? So those are the things about the properties of a z-score. Now, let's say I had a z-score, but I wanted to find out what the raw score was. You know it. Right? Let's say somebody has an IQ of 130. Well, 30 is how many standard deviations above the mean? 2, right? So I know, oh, I think I said that backwards. Did I give you the IQ of 130? Yeah, sorry, brain is Monday morning. If somebody told me they had a z-score, their IQ was 2. Right, we work backwards. Well, I know that the standard deviation is 15. So 2 times 15 is going to be 30. Above my mean is 100. So I know that their IQ is going to be 130. Now, this is just the formula for doing it. Right? 2 is my z-score times 15 plus 100 equals 130. So either way, you can go in either direction. Now, another thing we can do is we can transform scores from one distribution into another. Because sometimes, even though I can take my scores and I can put them into z-scores, sometimes I don't want them in z-scores. One reason is they don't like giving people scores in negative numbers. Right? Like if I gave you your test scores in like negative z-scores, I don't think that would be fun. The other thing is that it's a very compressed distribution. Most of the scores in a z-score distribution are going to fall between plus or minus 2.5. All right? So it's a very compressed distribution. So often we want to express our scores in another distribution. Another example, here's, let's say I develop an IQ test. Right? I could do that. And I make it out of 50 points. But typically, IQ is expressed as 100 with a standard deviation of 15. So if I want my IQ test to be comparable to everybody else's, I might take my values and express them in this new distribution with a mean of 100 and a standard deviation of 15. Okay? So how do I get there? How do I get there? Well, the first thing I have to do is I have to take my original scores and find their location. That is, find the z-scores. Right? So if I find the z-scores, then I can re-express them in the new distribution. So let's take a look at this very quick example. Okay? Let's say I want to transform my scores. And these scores, this is like these 4 people. Let's say we have here an n of 20. So 20 people actually took this test, but we're only going to do 4 as an example. All right, so Anne, Bob, Carol, and Diane, they took this and they got these scores that has a mean of 6 and a standard deviation of 3.18. But I would like to express them in what are called t-scores with a capital T, a capital T. And those t-scores, a distribution of t-scores typically has a mean of 50 and a standard deviation of 10. That's its definition. Again, sometimes we put these things because they're standard ways for people to compare them. So a mean of 50 and a standard deviation of 10. So the first thing I do with Anne's score is I find out what her z-score is. Okay, so we do that easily. Now again, get used to the idea of having some kind of quick estimation when you do this. It'll save you grief if you have some idea of what your number should look like when you do this. So we know Anne is going to be positive. She's above the mean. Also, right, she's 10. So, and our standard deviation is 3.18. So we know she's going to be more than one standard deviation above the mean. So fine, we figure out the number. We find out she's 1.26 standard deviations above the mean. Good. Now, if I want to transform it into my new distribution with a mean of 50 and a standard deviation of 10, I just use the other formula, right? Because I say, okay, she's 1.26 standard deviations of the mean. What's the standard deviation in the new distribution? 10. 10. So it's 1.26 times 10 plus the new mean is 50. So that's where we get the 62.6 from. Does anybody have questions? Not sure where something's coming from? Yeah. Can I what? Well, this is what this x means is just a transformed score. It's just a transformed score, right? Because I'm transforming my scores. I'm taking a z-score and I'm transforming it into a new distribution. What's my new distribution? It has a mean of 50 and a standard deviation of 10. Yeah? No? Better? Okay. All right, so let's just do that for these people. Get in a little practice here. All right, Bob. With Bob, what's your estimate? Just without doing the math, what's your estimate? Yeah, right? It's going to be a little less than 1. But also positive. Right? So he's almost 1 standard deviation above the mean, which means that in terms of t-scores, approximately what's his score going to be? Don't do the math, just to estimate it. It's about 60, right? Okay, just so that you have some idea of what you're doing. So let's get his score. Right, my z-score times my standard deviation plus the mean. Okay, so let's do it for the other two as well. Carol. Okay, without doing the math, what's Carol's z-score? You know it. Yeah, negative 0.94. Why? Right. Yeah. Right. She's just as much below the mean as Bob was above the mean, so it's going to be the same. Okay. And then just the last one of Diane. Right? She scored 0.31 below the mean. So you know it's going to be below 50. Yeah. it's just a given of the example. T-scores, that capital T, it's a common distribution. So we just went with that. But you could transform it into whatever you want. Yeah. Yeah. Questions on this? Other questions? Pretty clear? Okay, good. Now, where are we going with this? We're going to wind up using the normal distribution, okay? Because where we've been heading with all of this, with all of these numbers, is, again, I want to know how probable a result is, right? Because this is how, kind of in a nutshell, this is how people make decisions about various things. Let's say you give one group a drug and one group a placebo, and you get their antidepressant scores afterwards. So the question is, how likely is the difference between those two scores, right? If the difference is very likely, then we say it could be due to chance. But it's very unlikely. If the people taking the drug got such a low depression score that that's very unlikely, then we say, oh, it must have been due to the drug. You know? So this is where we're trying to go with this. So we're getting these numbers. We're transforming our numbers. And now we have to talk about what are the distributions that give us these probabilities. Okay? The typical one that we all have seen is the normal distribution. We know the shape of a normal distribution. Right? And the truth is, everybody talks about the normal distribution. There is no the normal distribution. There are a lot of variables that are normally distributed, meaning they have the same characteristic shape. But the means and the standard deviations are different. So for example, height might be normally distributed for a given group, or weight might be normally distributed. But the means and the standard deviations are going to be different. The shapes will be the same. And that shape is important to us. Why? Because the area under the curve is going to be probability. That's why. The area under the curve is going to be probability. So by making reference to a normal distribution, we will be able to find out the probability of things. Okay? Now, a normally distributed variable that has a mean of 0 and a standard deviation of 1. Okay, normally distributed, mean of 0, standard deviation of 1. That's called the standard normal distribution. The standard normal distribution. The standard normal distribution. Mean of 0, standard deviation of 1. It's a normal distribution. The shape is normal. Because again, right, not all distributions that are put into z-scores are normal. But if you have a normal distribution with a mean of 0 and a standard deviation of 1, that is a standard normal distribution. Okay? So take a look at this for a minute. This is a picture of a standard normal distribution with the areas shaded. Now what we're going to do is actually we're going to make reference to tables in the back of the book that have real specifics, but we can get some kind of basic idea over here. Now, the area, the total area under the curve is, it's 1. It's 1. The mean cuts the distribution so that you have 0.5 on one side and 0.5 on the other side. Now, look at this. What this means is, right, because on the x-axis here is z-scores. This means that between one standard deviation above or below the mean contains essentially 68% of the scores. That's why it's very compact. Between one standard deviation above or below the mean contains about 68% of your scores. Okay? So for example, let's go back to our IQ of 130. What was the z-score for an IQ of 130? 2, right? Okay, where is 2? Well, it's here. How likely is it to get a z-score of 2 or higher? Well, you know what it is? It's this area under the curve. So is that a likely event or is that an unlikely event? Seriously unlikely. All right? So that's what we're doing. So this is what we do in statistics, and it's going to be some variation on this theme the whole semester. We take our raw scores, no matter what they are, and we transform them, not always into z-scores. This is what we start out with, but it's the same basic idea. We transform our scores into a variable whose probabilities we can determine. Right? Because it doesn't make sense for me to have a probability table for every single variable. Right? If height is normally distributed and weight is normally distributed and I don't know, a whole host of things, IQ is normally distributed, it doesn't make sense to have IQ tables and weight tables and height tables that have the area under the curve. All we need is one table, the standard normal distribution. So we transform our raw scores into z-scores, and then we can find the probability of our result. And then we make decisions about whether things are different, whether they're due to chance or not. But some variation of this theme is going to be for the whole semester. You're going to learn different details, different tests, different numbers of groups, but the basic idea stays the same. We take our scores, we transform them into scores whose probability we can find out, and then we make decisions based on that. All right? So when we talk about, I just want to see something. Okay. I think I just said all of this. Let's just check this for a minute. Yeah, standard normal distribution, yada, yada, yada. Proportion and area, area equals curve. Okay, we said all of this. So there's different ways to do it, right? It depends. If your variable is discrete, there are certain ways to get the probability. That really speaks to non-parametric statistics, and we'll talk about that at the end of the semester. What we're going to be dealing with are continuous variables, essentially continuous variables. And then the probability is going to be area under the curve, but not exact points. Ranges. Ranges. Let me bring back the distribution again. Or I could just draw a picture. Okay. What we're going to be doing a lot of is, let's say, finding areas like this. The probability under the curve is going to be, right, if I want to know the probability of a result from here to here, it's going to be that area under the curve. And that's what we're going to be doing, is finding those areas under the curve. And it's very simple. And what's the last thing I want to say about this? Just understand something. Understand something. What we're doing is we're taking real distributions, real data, and comparing them to theoretical distributions. Like a normal distribution. What's a normal distribution? It's bell-shaped. It's asymptotic. What does asymptotic mean? Yeah. Yeah. It keeps going, but it never actually reaches 0. Right? It's because it's an ideal curve. It's a theoretical curve. Whereas, when we're measuring real data, there's actual points where it might be 0. So what we do is we compare our data to these theoretical curves. There is some error, but depending on your sample size and a variety of other things, the error is small enough that it's good enough for our purposes to get a basic idea. And so that's what we're going to be doing. And I actually think that I want to end there. Yeah, I think I want to end there because I don't want to start the next topic as a big thing. All right, I will see you guys on Wednesday.